Okay, physics students, Mr. Phelps here. I'm your physics teacher. So I noticed that there's some really difficult activities for the physics, especially Unit 1's quite involved. So I want to spend some time going over it to help you guys out because not one of you has done it yet. And honestly, I really can't blame you. It is pretty difficult. And looking at myself, I thought it was pretty complex. So it's called Kinematics 1, end of Unit 1. So jump ahead a little bit. And of course, objectives. I'm sure you guys always read those. Introduction, I'm sure you guys read that as well. So here's what my grading criteria is. All teachers have this, so that's how I'll grade you. It looks pretty simple. There's actually quite a bit to these. Next, so you guys will have to watch a video. So up here it says car round trip. Click on that first task 1. What you get is this right here. And there'll be a picture of a red car. I'm not sure what kind of car it is, but you get the mass right there, which I don't think they're right to worry about in the calculations. It's not really important. The distance is all going to be covered. And over here, the most important part of all this is going to be these numbers here. This is the time the car is proceeding through its path, and it's going to 15.8 total seconds. The x is how far the car travels, so that's in meters. And then notice eventually gets into, okay, it starts decreasing. All right, there's a reason for that in a second. And your velocity is increasing, not real fast, but these are all meters per second. But notice later on it becomes negative. A negative velocity means you're going backwards. So positive direction is going forward. If it's negative, you're going to have a reverse. And of course, acceleration over here, a sub x. All x means in the x direction along the y, like an xy axis. So you go from left to right. Just think left to right is your x. Okay. So of course you have acceleration over here on this side. All right, now let's go to the questions. So let's go to question 1. So you got to, all you have to do is here describe what you see take place in the video. Don't give me just one sentence. Give a little more detail what the car is doing. In fact, let's watch together real quick. So let's put that back up there again for you. So watch this. Yeah, see the car is moving. They're hitting the gas. And at some point, ooh, it stops. And then it backs up. There's reverse direction. You're accelerating. And the graphs, you have 3 different graphs right here showing you. So the time versus left to right motion right here. You have the time versus the velocity. You also have down here the time versus acceleration. All right, so that's become important for later on. So those graphs for later. So we move back into our questions here. Let's go to question B. So you have 5 distinct periods taking place in your motion. So the first one's given to you between 0.2 and 4.6 seconds. You increase speed in positive direction. Numbers you're going forward. So we look at that in the video. So let's go back here. 0.2 right here to 4.6 down here. You're increasing speed. Okay, well, actually you're covering more distance, but here's the speed over here. You're getting faster and faster. Okay, so it goes from 0.03 at 0.2 seconds to at where does it start to level off? And then go to 5. Let me see where to go. 5.31 at 4.6. And then you notice after 5.31, its highest speed, what happens? It's going to get slower. So there's another distinct period of time right there where the car is changing its velocity. Okay, so you got to stipulate that time frame in here somewhere in these seconds. And then you're going to have down here what's happening in this area right here. You got to talk about that. There's your velocity. Here's your time. There's a third one right there. And then remember, it's negative. If it's negative, you're going backwards. All right. So you're going backwards here, and you're going fast, slow as you go backwards. Okay, you got to think about that. Now, there's a certain time frame that happens, and you can see it's a pretty wide frame. Then your fourth one, there's that 4 or 5, I forget. Then here, what's happening right here? Not a whole lot, apparently. There's not a great deal happening in this area. So it's about the time frame that takes place in. Okay, it's not a lot of change. Looks like it doesn't really change the speeds in this at this point. So you got to think about that. Looks pretty consistent, pretty constant. All right, so let's go back to here. So using all that, so you describe increasing speed, decreasing speed, positive direction, negative direction, and or is it constant speed? And give me the time frames for those. Now, that shouldn't be too bad. That's one of the easier things you have to do. Now, part C. Part C involves for each time period, we have 5 different time periods we talked about from above. So you can take the stuff up here, this area here, and apply that down here. And so put the time periods there as well, same ones. Talk about displacement in X. So you look at the graphs we had earlier. So what's taking place in these graphs? So for instance, X. Let's go to that real quick. Where'd it go? All right, so this first graph right here is what I was talking about. So let me draw on this a little bit. Let's go. Let's reuse red. So in here, notice you're increasing speed as you go up. So you're getting faster and faster. So talk about that. So between 0.2 and 4.6 seconds, what's the car doing? Was it going forward or is it going backwards? You got to think about that. And is it accelerating or not? Okay. And now just and why? What's this graph tell you? What you seen right here that tells you that? Pretty obvious. Okay. Okay. So and then in this area here, talking about what's happening here, this area. So right here, it's those dots getting closer and closer. These are pretty far apart dots. Okay. But over here, then they're getting a lot closer together. Okay. So what's happening speed here? And then what happens at the top up here? So this area right in here. Let me erase some of this. Not too much. A little busy there. Okay. So then up in here, what's happening to those dots here? And then down here, green. So those dots here are starting to get spread out a little bit. They're getting farther and farther apart as you go down. So for that part of the graph, those 5 sections, what's happened to each of those 5 areas that you stipulated back in part B? Okay. So looking for words like forward, backward, stopped. Let me see what else I'm looking for here. Yeah, graphs, and on top of the graph, is it going up, going down, that dots get close together, getting farther apart, things like that. All right. Now, for this graph right here, notice that's for the velocity. So this is your displacement, how far the car is going for every 2/10 of a second. So this is called displacement. That's what X represents. Here, this is velocity, is actual velocity. So the car here, talk about what's going on there for the first segment. Talk about what its velocity is initially, and then what's going on to its velocity as it goes through. What else we got here? Oh, and here, what's happened to velocity right up there at the very top. Okay. And what's happened to velocity here and in what direction. Okay. And also, talk about velocity at this spot right here. What's going on at that point right there? Okay. So what's actually taking place there and what's taking place down here to velocity. Okay. So then also just talk about that in under Vx. And over here, this one over here, the velocity, not velocity, but the acceleration at given times. Okay. So here looks like it's accelerating, maybe slowing down a little bit. Maybe it came to almost a stop right there, it's slowing down. Then once it happens, acceleration over in this area. Okay. So we're going to talk about acceleration. I'll be pretty lenient on all that. What I'm looking for right there is velocity, is it increasing, then acceleration decreasing as well in a positive direction, or if it's decreasing, the acceleration is negative. So if it's getting faster, if velocity increases, you're saying acceleration increases. If you're saying velocity decreases, you're saying acceleration is negative. Okay, so keep that in mind in your answers there. Okay, so I'll be pretty lenient because your word, you have so many answers. You have a lot of different answers for this. I mean, it's pretty in-depth answers, what I should say. So I don't expect you guys to answer quite that depth, but just put a little thought into it. Okay. Now moving on. Let's go to. Let's see how that's this. All right. So change screens. In my opinion, is easily the most difficult part of the assignment. I did not enjoy this myself, especially the last 2 lines. I'll explain to you in a second. Let's see. Oh, right there. There it is. So in this portion right here, you'll see the one I'm looking for. So up there, actually up there is what I should say. use the data up there. Now, going back to here. So, what you got to put down, like right here, I'm looking for here, it tells you between 8 and 10 seconds. You guys are supposed to have done your assignment about graphing, and then they're supposed to talk about interpolation, extrapolation. Hopefully, you guys read that and went through all that. Anyways, so right here, I'm looking for, I want the recorded activity time at 7 seconds. You got to look at 7 seconds, your data, and I want the x value there. And then over here, I'm going to look for the velocity, or v sub x, meters per second there. Over here, I'm going to want to see my time at 9 seconds. So 7 seconds, 9 seconds, and sorry, what is it? 7, 9, 8, and 10. So I want 7, 8, 9, and 10 seconds. That's first four. Find the data off the data table we showed you earlier when the card is in there. And then that's pretty easy to record that. Now the hard part is down here, the last two lines. You need the interpolated time for 8 seconds, which between, so it'd be right there, 8 seconds, and down here would be for 10 seconds. This will be extrapolated. So interpolated here, extrapolated right here. In fact, here you want to interpolate, like I said, for 8 seconds and extrapolate for 10 seconds. So put the data over there. Now, let me go through. I'm going to pause this for a second. I'm going to display it. I actually do the calculation myself to show you guys how to do it. So give me a second here. Pause it. All right, so I'm back. So right here, this fifth line or fifth row, you want the interpolation at 8 seconds. So the calculation to find displacement meters for there is going to be, let me show you a picture. So there's my work I did. So you just copy my work. That's okay. It's pretty hard calculation, so I just set it up for you. So you want to set X, which what we're looking for is how much displacement you're going to have. This is for a linear. Try to prove if this relationship's linear for displacement or not. So there's your calculation. So define it at 9 seconds, because an interpolation means a point between two other points. So 9 and 7 are on the other sides of 8, obviously. And there's the data, the displacement for 9 seconds and for 7 seconds. So put those in, and then we put the 8 right here, and then we subtract from 7 seconds. And then from there, you should get a value. And then you're going to put that value in, let me go back to this, in for right there. For the velocity, or v sub x at that point, next picture I want to show you. So I put the acceleration values for 7, 9, and 7 seconds here. Pretty much the same equation. I just put the accelerations in for 9 and 7 seconds. And then, of course, I put the 8 seconds looking for compared to 7. And let's do the math right there. So there's the equation. Use that. From there, you guys should be able to find the value that's going to go right there. Okay, so once again, the picture right there, there's the equation. You can pause it and just go to that picture and do the calculation and put the answer there. Now, the extrapolation at 10 seconds, remember extrapolation is a point outside two other points, trying to extrapolate what's going to happen later on. So for that, all I have here, well, you would just do the calculation. Let me show the calculation to you, which is the one. No, that's not the one I'm looking for. And that's one right there, actually. Yeah, that's the one. So there's a calculation to find for displacement if you extrapolate at 10 seconds. So going beyond the 9 seconds. Now, we already have it. You might be thinking, we already got a value for 10, don't we? We do, but we're trying to prove if that, because that shows what really happens. But this shows what, if it's linear, what would happen? It's linear equation. So if it actually is true, if it's linear, then it should get the same answer. If we get a different answer, that proves that it's not a linear relationship. The displacement, how far the car travels in a given time. Now, once you have that done, then you have to go to, let me see here. Then you're going to go to the last calculation, which is this, to find the acceleration, or I'm sorry, the velocity, is what I should be saying. No, it's actually acceleration. I put v sub x, but there's calculation for the last column for the last row. Again, it's pretty much the same calculation earlier, but we use 10 seconds here. And get your answer there and put that in that blank. So it goes in this last blank right there. Okay, do the best you can. All right, I'm looking for specific numbers, but if you're very, very close, I might just give it to you. Okay, so I'm gonna go back to the picture real quick. Make sure you guys have that. There it is. All right, moving on. Let's see, let's pause this. All right, so for part B now, using data which you found above, you're going to, let me see, I'm going to extrapolate, not even close. Yeah, you should actually find the values that you get in your answers are not even close to what it actually shows on the actual data. So it tells you the relationship is not linear. Okay. All right. So at that point, so between 7 and 10 seconds, both graphs basically have bends to them because you are slowing down. So it makes sense. It's not linear. It's not a constant velocity. All right. So this part right here is trying to describe describe the base assumption behind interpolation or extrapolation. So maybe go back to your unit and find out what it was about graphing and see what it says about what interpolation is, extrapolation is. Just basically define what those mean. And then for at least like one of those values, explain why the calculated value was larger or smaller than what it's supposed to have been. Well, I kind of gave it away earlier, didn't I? Okay, so why is it different? So we got to about linear, is it not linear? What's taking place there? Do your best. It's not an easy thing to answer. All right, next. So again here, you get two different balls. You might have taught this in school before I started doing this, but you drop two different sized balls and say the exercise ball, which you guys are putting the exercise ball up there, it can be very heavy. See, it's 3 times larger in mass and also how actual physically big it is. Which two balls would hit the ground first? So you can hypothesize about this, describe your reasoning, why you think one will hit first or they'll hit at the same time or what you think is going to happen. So describe why. They'll try to get as much detail as you can. I don't want to see just 1-2 sentences. They're a little more detail, okay? Now in part B, let me see, part B. All right, so you see for the ball drop, you guys got to click on this, and that'll open up something for you. So when you click on the large ball drop, you get this right here. So we click on this. There's your data, and there's your graph. So I'm looking for directions here. Talk about for ball drop 2 experiment, observe the graph. You have the vertical displacement, so up and down, basically, of the small ball versus y versus time. So I want to see, what can you say about the vertical or up and down motion, or the y direction of the small ball? What graph shape is it? What's the shape of the graph tell you about the relationship between y and t? So if you look at the graph, it looks like it's curved, isn't it? So there's something right there. It's curved, but notice the displacement is always accelerates at the same rate, but it looks like it's covering more and more distance as it falls. It's basically accelerating. So it's got the same acceleration all the time. So I'm looking for my answer there. Once again, is the shape of the graph I just mentioned a second ago. It's moving farther every second. It's going every tenth of a second. It's going a little farther all the time. It's increasing its distance it's going to cover every given second because it is accelerating. All right, and also let me see. Yeah. So if we look to talk about the graph shape and then what's taking place, displacement, and so on. There you go. Then we go to the other graph, because now in part C, looking for it there. So observe the graph, the vertical velocity, so v versus time. So yeah, this graph right here. So click on all that. What do you observe about the vertical velocity of the ball? All right, so vertical velocity is, well, it's going, if you notice, should be getting faster, okay? But it's getting faster at the same rate. So again, it's consistent acceleration. Look at the graph, right? And then, so it looks like the velocity is pretty much, it's consistent. Velocity is increasing, but it's proportional time. The more time it goes on, the faster it gets, which makes sense, okay? Now, and also may describe the shape of the graph. Is it curved? Is it linear? I'm kind of looking for something like that in the answer. Now, part C is talking about down here, actually. So I want you to compare the graphs for the large ball and the medicine ball. So I go to the graphs here. So here's the large ball. It tells you in part C, click on the Y label on the vertical axis, which is right there, and velocity components. So we're going to compare this graph. So click on the Y. Actually, not the Y. We'll click on the, yeah, and want V sub Y. So V sub Y, right, so where'd it go? Right there. So we compare that graph to this graph. So that's for the smaller ball right there. So that ball was only 0.58 kilograms, 12 centimeters. There's the other ball, which is, pull it back, a lot larger, almost 4 times mass and almost 3 times farther around. It's a bigger ball. If you notice though, what's happening? Look at these graphs. So time versus velocity there, and then this graph, time versus velocity here. They're pretty much the same. So what I'm looking for in part C then is what is the relationship between the velocity and time for both balls. Okay, so yeah, let's try to describe that as best you can in part C. So what's the shape of the graph and how are they related to the velocity and the time, how they're related to each other. They have a lot in common. Okay, now for part D, you're going to compare the time versus displacement for the first ball, the smaller one, and then for the large ball. So if you see the y, the displacement versus time, those look the same. And if we did the velocity from earlier, once again we did earlier, we had, well, not that. We want the other one we had earlier, which was the, that we had. And we also had the other ball. Where'd it go? Where'd it go? V sub y. So it looks like they have a lot of things in common. So if you get the same things all the time for both kinds of graphs, then what you're looking for is what's that tell you about their how their falls relate to each other. All right, so it looks like they're pretty much, well, you can tell yourself. So how are they related mathematically? Is there a much difference? All right, are they different even at all? So talk about that in part D. Now for part E, it's looking for between 0 and 1 second, the small ball and large ball, how much displacement was there? And then you're trying to find the velocity. And so if you look at, well, the small ball at 1 second and the large ball at 1 second. So we go to the large ball at 1 second right here. Looks like 4.81. And if we look at the small ball, which is right there, at 1 second, 5.045. All right. So then you get a calculation you got to do as well. You got to take the change in y, all right, divided by the time. Well, this time's easy. It's 1 second. So basically, all those are going to be your velocities right there. So that makes it much easier. So just take your displacement, what you got for the middle column, and just divide by what you got for the time, which is 1 second. So that makes part E really easy. One more thing for part E, make sure when you put that change in y, that triangle symbol with velocity, you can actually put the meters per second, okay? M/S, you gotta have a unit for that. And last for part E, again, a question asks you which ball drops faster. So it should be pretty easy to find. It's not a huge difference, but there is a difference. One ball does definitely fall faster. So stipulate that and you answer E. All right, now for part F, you're going to find the velocity of both the starting velocity for at point, well, not really initial, but starting at 0.1 seconds. All right, so if you look at the small ball, oh, let's see, let's go back to, let me pause this. So for the large ball, if we look at, let's see here. Hold on. So at 0.1 seconds, let's circle this for you. So 0.1 seconds, it's right there. All right, so it looks like 1.36 at 0.1 seconds. And then look at the other ball. So hold on, same one. Those are the same graph, aren't they? Hold on. All right, now we're back on track. Screen froze me a little bit. So for the ball drop, for the smaller ball, at 0.1 seconds, 1.321. And for the large ball, at 0.1 seconds, we're seeing 1.36. So not a lot of difference right there. Now, from there, you must find the final vertical velocity. So what you're going to, well, that's given to you at 1 second. So down here, 9.07 for the large ball, and at 1 second, and 9.614. Right from there, what you got to do is subtract the two, because it does tell you in the equation you want to take the change of velocity, so and then divide by the change in time. So the time is not 1 second. Between 1 second and 0.1 seconds is 0.9 seconds. So if I put my calculator out real quick here, watch this. So for example, you have your 9.61 seconds. Make that negative, and subtract from that 1.32. Make that negative also. Now, that's not your final answer. That's difference in velocities for the small ball between 1 and 0.1 seconds. Still got to divide that by how much time passed. So still got to divide that then by the 0.9, which you guys, I'm not going to give you all the answer. Just get you set up just to divide that by the time period. Then do the exact same thing for the large ball, okay? And then that takes care of part E. Now, by the way, for the acceleration in the last column, you're trying to figure out, make sure it's meters per second squared. So ms squared when you type that in there, okay? Next, last part. Also, one more thing I forgot for part F. The velocity, the acceleration you're supposed to be looking for is desired to be 9.81, it says in the comments. So it says, how does the average acceleration of two balls compare to what's supposed to be 9.81 meters per second squared? All right, so compare what you got with those for the two calculations did, and how do they compare to each other? All right, so you got to discuss that in your answer as well. So don't forget that part. So after almost half an hour talking to you, part G, last part. So it says, based on what you've done the videos and the calculation you've done, why do you think the vertical acceleration, so how fast it falls, the rate at which how fast falls, the acceleration are not equal to what's supposed to be, which is actually 9.81 meters per second squared. So why is it different? Well, that's actually 9.81 is based on having a frictionless environment, a vacuum, if you will. So we all know there's not a vacuum around on the Earth. We actually have air. So maybe use that as part of your answer. Also, what you say about the other prediction about the ball will land first. So you made a prediction earlier about which will land first. So if you're wrong, you pose why, a rationale to explain why you're wrong. Okay. So just give me at least 3 or 4 sentences here, minimum, to explain what's going on. All right. So it shouldn't be that hard a question. At least no math involved with this one. All right. So I'm done with this screencast, my first one. I know it was a little hard to follow. Wasn't the easiest thing to do. Hopefully you guys do okay with it. It's better than nothing. All right. Please contact me if you have any questions. I'll do my best to help you out over the phone. All right. Thanks. Bye.